So Dr. Thornett and Jason Burnfield are going to present to us, and so you can. I'm going to go ahead and switch our view in this room. I'm going to hope that it doesn't interrupt a lot. Give me a minute while the system switches over from us being the lead versus you being the lead. I can still drive the slides though, Dr. Thornett.
Oh, I like there's something called Sir. This isn't happening in the UK.
Yeah,
You're very polite there in America. Right. So hang on. I've got a table here that's got so much stuff on it, I can hardly move. Okay, right. Well, thank you very much for inviting me to come and talk today. So it's part of two talks. We've got myself and Jason together, and Jason may well be making some comments as we go along in this first talk. Just to say, whether you stay and listen to my talk, which would be very nice if you could, but definitely you're going to want to come back and hopefully and listen to Jason's talk there. I'm just trying to find if I can clock a second so I know what time we're going on, but seem to have lost it on my computer. Excuse me. There we are. So I'm going to talk first. We're both talking about the 20-meter Skynet dish to give you an introduction to it. I mean, there was a bit of introduction yesterday on pulsars, which was quite stunning, obviously quite at a high level. This is my first talk here is about perhaps a little bit more basic stuff that you can do with the telescope there and to get yourself introduced to it. My local astronomy group, they mainly a lot of astrophotographers, and some of them have got remote telescopes in Spain, where I'm based in the UK. Where it's sort of sun shines a lot and there's not much cloud, unlike us, and they're very proud of their remote telescopes. But me, I go in now and say my remote telescope's 60 foot in diameter, so I can beat them hands down. So if nothing else, it's a little bit of a way of showing off. You might wonder, this particular picture's got nothing to do with the 20-meter. It's actually come care of Jason, where he works there at the VLA. There's a few of his pictures splattered around. I thought they're pretty good. Anyway, so I'm starting off with the integrated hydrogen spectra of galaxies, as you can see there, basically where the field of view of the telescope encompasses the entire galaxy. That's basically what it means. And so I hope you'll find this interesting. So now it won't go to the next slide. Why is that? Come on. There we are. So I'm going to start off with a little bit of an introduction to how you actually take an observation on one of these scopes. So on this particular 20-meter Skynet dish, if you've never done it before, not a terrible level, but just to give you an idea how to approach it. So here's a picture of the thing. And I think it's absolutely stunning that all of us as SARA members can access this. Up until, I'm not quite sure when, but relatively recently, if you weren't an American citizen, you weren't allowed to. But I'm very grateful, not being an American citizen, that this has now changed and everybody can do it. And then when Jason and I managed to use up all the credits for the first time ever, I was also amazed that SARA went and bought a few more credits and didn't criticize any of the observations that we took. So thank you very much, guys, for letting us do that and get so involved. It's brilliant. I think I've spent far more on this scope, far more money than my membership cost. So when you actually do an observation, so I'm missing a slide there. Oh, fair enough. When you do an observation, you pull up the website. It's all done through a web portal, and there's a single login set of details which every member of SARA uses. So this means that you can actually see other people's observations from SARA as well. There's also a number of observations which the people at Greenbank do sort of centrally, which anybody can access, whether or not you have an account. So even if you're not a member of SARA, the number of things that you could download and have a look at and process, and sort of get your your sort of hands and feet wet if you want to. So it comes up and shows a little map like this, and you can then decide where you want it to observe. Sorry, that's just a picture of the front page on their portal. I thought I had that in it. Yeah, and this is a list of observations, which you can see why I'm grateful that no one's criticised me, because you probably noticed that every single one of those observations is mine because it's got AMT written at the end of it. This is how you actually define who's done it. You put your initials at the end of it. And this comes under it. There are non-radio dishes at Green Bank, which also come up under this, but we don't have an account for those. So I was saying, back to where I was. So when you want to do an observation, you pull up this particular page, add observation, and you can see there that you can add in the right ascension and the declination, and give it a name where you put your initials afterwards to show that it's yourself, and various bits of information such as how close you let it go to the sun, etc., and how high above the horizon it needs to be. And there I've added in, I think this might be an M31. So yeah, one of the M31 ones I did, and you can see there the right ascension declination has been now added in at that point. And I included this little slide because it's at the bottom of the page. You get this particular graph, which is quite convenient because it tells you at what point the target you want to observe is going to be above the horizon and above your whatever cutoff you've used for the elevation. And so it tells you how long you're going to have to wait before you get your observations. So that's quite handy. And then when you've finished your observation, it will come up and just summarize everything for you. So here you can see I've chosen 1,420 megahertz. And my observations are 1 second long, 1.0. And they integrate for a second as well. And then I repeat it 5 times, and then it sort of adds them all together. If you're not used to using a telescope this big, you'll be shocked at just how short the observations are. With our backyard things, we might be doing things for a few minutes, and here we are with just 1 second observations. It's really, really quite weird. So this slide is just to show you the general settings that we're using for many of these observations. And I think Jason, you wanted to say something here, didn't you?
Yeah. So this on-off mode, the way we pull out, so when we're looking at hydrogen spectra of galaxies outside the Milky Way, those signals are very, very tiny compared to the Milky Way signal itself, which is pervasive in every direction. Even if you're not looking in the plane of the Milky Way, the hydrogen's still there. And when you're talking about the relative size of that signal with respect to an external galaxy, it's like hundreds of times bigger. So even if you're looking straight out of the, straight into the darkest part of the sky where there's not much hydrogen, we're still sitting inside a giant cloud of hydrogen. So one of the ways to deal with that is to use off-target sky near the object as your calibration reference. And what that does is it subtracts out most of the Milky Way signal so that you can focus on the part of the signal that's coming from the external galaxy. And so we use on-off mode for that. And what I was going to add is that I was having some trouble with on-off mode working correctly a few weeks ago. And I think it was actually unrelated. I mean, there was some communication issues with the dish that Green Bank had to sort out. So I think it's working fine again. But during that time, I switched to using just tracking mode. And what I did is I just did a single observation manually off target and used that as a calibration reference. But I did all the calibration, during the post-processing, and that worked just as well. And actually, I ended up switching to that mode for when we were doing our mapping exercise, which is going to be the next topic, because it was also more efficient to just do a single calibration and then do all the other single point observations and just compare them all to that one reference. And that way, because we were doing a bunch of points in our mapping exercise, and I wanted to be as efficient as possible. And that did work well. So yeah, you can use on-off mode, or you can use tracking mode and just get yourself a manually set off-target observation to use as your calibration.
Okay, thanks, Jason. I just noticed that unfortunately the presenter view, and I do apologize, guys. Just managed to get rid of that now. Anyway, so we thought I'd give our survey here a little bit of a name, LRO Skynet 1. And in terms of the galaxies that we've chosen for this, we've gone back to the Things survey, which I know many of you will know about. But there are a number of galaxies that Walter and co. Used here, so I thought it'd give us a good point to start, because they were likely to give some good results. So I'll just talk through some of the results, because again, this is a little bit surprising when you're just used to backyard scopes, as I was, when you start seeing these things as they come through. Here's most of this we did analysis in Excel, so you can see an Excel spreadsheet there with the data as it comes through, and one of our graphs on the right hand side. And what I've done here is I put a circle around the galaxy that we're observing, which is the black circle. But the purple circle is actually not the galaxy that we're trying to look at. That's in fact actually the Milky Way, because anything that we look at that's extragalactic is still having to go through some element of the Milky Way to get there. With a backyard scope, unless you're looking at the into the disk of the Milky Way, you usually wouldn't see very much. But here, it still shows up in our observations. And on the bottom, we have velocity, which is, I think it's kilometers per second, isn't it, Jason? Yeah, that's right, kilometers per second on the bottom.
Yeah,
and
that's correct.
Yeah, and on the left-hand side of intensity measurement. So if you look by that kilometers per second on the bottom, the 0 point, which is just above the O of smooth, is where things are not moving relative to where we are. And as you can see there, there's some Milky Way moving slightly towards us at that point, looking in this direction, whereas the galaxy that we're looking at here, which is NGC 5457, has got a largely positive, well, it has entirely positive velocity movement compared to us, and that's because it's moving away from us.
And I would just add the Milky Way signal that would be in the raw data would be hundreds of times bigger than the external galaxy signal. But that little dip that you're seeing that's actually negative, it's just a residual left over from the fact that the off-target calibration signal, the Milky Way signal must be slightly larger off target than it is on target, and so it leaves a slight negative. So all you're seeing is the residual difference between the Milky Way signal on target and off target. And it's never exactly the same, so you're always going to get a little bit of a blip at 0 or close to 0.
Yeah, thanks, Jason. So again, here I've put a number of galaxies just to show that same effect coming through there. And you can see, depending on which direction we're looking in, the Milky Way signal may well be positive in intensity or negative intensity, depending on, again, but it's moving, how it's moving relative to us. But you can see in all three of these cases, we've got galaxies that are moving away from us. Now, yesterday we had a discussion of the hydrogen line, so I'm not going to spend much time on this. Just it was meant for just be an introduction to where the signal comes from. But this slide is quite important. So one of the pieces of information that you get from the data relates to the angle of view, or at least the angle of slant of the galaxy relative to us along the line of sight. And you can see here that a galaxy which is more edge-on will have its blue shift and its red shift separated by a greater distance than a galaxy that is face-on. And this is something that you can see in the data. And here on this slide, I've given some good examples. So the signal that you get from these galaxies always demonstrates, or nearly always demonstrates, 2 peaks. And the reason it's got 2 peaks, one at either side, is because one is essentially one side of the galaxy that is relatively moving faster away from us or faster towards us compared to the other side of the galaxy due to the galaxy's own rotation. And here M31, which is relatively edge-on, has shown 2 widespread peaks, whereas M101, which is much more face on, you can see the peaks are much closer together. And when we get down to NGC 628 or M774, now you've got an almost entirely face on galaxy with two peaks that are pretty much on top of each other. So to finish off, I've just got a few examples of different galaxies that we observed. Again, you can see that in any of these galaxies, there's a range of velocities which will come from different parts of the galaxy and its movement. And this suggests to you that there's an awful lot more data within that than just which side's moving away and which side's moving towards us relatively. And you can see here that with M51, again, we've got quite a high velocity relative to us, moving away from us, to such an extent that on the graph as I've presented it, you can't actually see the Milky Way, and that's because velocity only goes down to 100 at this point. To IC 2574, we've actually got, well, looks like here, a much bigger galaxy, but actually on the y-axis, there's a much narrower range there because IC 2574 is not giving us a particularly strong signal. But again, you can see the two peaks there representing the rotation of the galaxy. NGC 628, again, the peaks are pretty much on top of each other here, suggesting that it's a face-on galaxy. Again, substantially with a positive velocity moving away from us. And move on to M81 here. So we've got the Bode's galaxies. Interestingly here with M81, this is a galaxy where its velocity is slightly unusual compared to the Milky Way, compared to the others, in that we actually have some element of the velocity which is negative and some element which is positive. So in fact, some of M81 is relatively moving towards us and some of it moving away from us. Again, another spectrum of M81. M82 is entirely moving away from us, with the purple again being the Milky Way. And again, NGC 3109, we've got two peaks pretty much on top of each other. And M74, completely on top of each other. M101 here. Now, contrast those, which are all moving away from us, with our local group. So there's M31 here, where you can see the velocities now are all negative, reflecting the fact that M31 is moving towards us. Likewise, again, M110, a large negative velocity. And again, this is a face-on galaxy, so we don't see two peaks. We see them on top of each other. Again, another M110. IC10 again. And there we are. That's the end of my presentation. Thank you very much indeed. Another picture of Jason to finish you off with his bagpipes there. Thanks, guys.
Well, thank you. Any questions for them?
No.
Go ahead, Jim. You got a question here?
How do you subtract out the rotation of our own galaxy from your observation of the movement of the other galaxies?
Would you like to have a go at that, Jason?
Yeah, so generally they when in the professional world, I was wondering that myself when I first started looking at galaxies outside the Milky Way. The convention is that they don't subtract the rotation of our galaxy. They just basically they consider the solar. They basically just measure the radial velocity with respect to our local standard of rest within the galaxy. So I guess you could do that, and I guess get the radial velocity with respect to these, to the center of our galaxy, but that's not typically They don't do that in any of the professional surveys. They basically use I like either the barycentric correction or the local standard of rest. And actually, those two corrections are very similar. The difference is whether or not you account for the extra 10 kilometers a second the pro that represents the proper motion of the solar system in the local neighborhood. So the I believe what they call the barycentered correction just removes the orbital motion of the Earth from the data and doesn't remove the proper motion of the solar system in the local neighborhood. So they never really nobody really accounts for the rotation of the galaxy itself. Because they just basically use our position in the local neighborhood as the reference point. So so yeah, so basically if you want to compare if you're doing external galaxy spectra captures and you want to compare your data against the professional survey spectra, you just use LSR correction and it matches. So I don't know. Does that answer your question?
Yes.
Any other follow-up? Galactic rotation? Some people
So
talk about that before, so.
could you explain the workflow from the 20-meter data to the graph that you got? The graph is at a calc graph.
Yeah, so what I do is I'll go into the observation and download the um the calibrated spectrum file, which is just a text file. Actually, it's just literally two columns. Well, it's more than two columns because they do both polarizations. But it's basically a list of velocities and a list of relative or in a list of basically intensities or power levels in kelvins. They actually they do it in temperature. So I just dump those columns into an Excel spreadsheet that I've created a template to do this. So so that I don't have to keep repeating myself. So I can basically just make copies of that. And what I'll do is I'll dump the raw data in, and then I have some additional columns where I will do I actually Andrew, would you mind backing up to one of the spreadsheets and I
Yeah,
can kind of
I was
talk to it?
thinking
'Cause
that
I
might be a
think
good idea. Yeah.
yeah, so just one of the ones that actually shows the columns, because I think there is one.
Yeah, I'll find it now while you're talking.
Well, I think on one of the slides, there's actually a snapshot of one.
Is there? Okay.
Yeah, I think on one of the early ones, it
Okay.
shows actually the spreadsheet.
Yeah.
Yeah,
Hang on.
yeah, yep. Well,
It's up here a bit.
yeah, it's one of the early ones. Yeah, there we go. Okay. So, if you notice all the way to the far right, just before you get to the actual plot, there's where it says second, first, zeroth. Um, so what I've done is what one of the problems you have with doing these kind of observations is even with a big scope like the 20 meter and with the sophisticated really high end receiver they have, the background still drifts, and so you end up with a background that's slanted and curved and not flat. um, and so sometimes it's necessary to do a background correction to flatten it and normalize it to zero. And so that's what this gives. So one of the first things I do is I'll take and I'll create a polynomial fit And it only goes to second degree. Usually we don't even need a second degree. Usually a linear correction is all we need. And oftentimes it's just literally an offset, just a vertical offset. So, but occasionally there is quite a bit of slant and we have to remove that. So, that allows, so I'll calculate the correction function and then I'll subtract that from the main data column, and then the result will be the corrected data. And then the other thing that I'll do is I'll do like a 10-point a running average to smooth it because there tends to be a lot of noise, or a lot of and a lot of we're at the high resolution mode, we're actually capturing a lot higher resolution spectral data than we actually need for the uh, to see the details in the spectrum. And so we can smooth out by doing the running average, we can smooth out the graph quite a bit and make it just look nicer and make the spectrum kind of show clearer. So that's kind of it's really pretty there's not a lot of processing. It's really just taking the raw velocity versus intensity column, and then taking that intensity column, doing a background correction if needed, and then taking that corrected column and then doing the smoothing function. And then I just literally do an XY plot in Excel, and that does it. And the thing, the raw data file does have both frequency and velocity already calculated for you, so you don't have to do that calculation. It's and it's already corrected for the local standard of rest as well, so you don't have to do that part either. Um, like we do when we're doing observations from our backyard scopes, where it's literally just the raw data with no correction. So.
Okay, thank you.
The other question in the room. Any other questions online? Hey, I have just a curiosity question. We did talk 20 meter yesterday as well, and so based on one of the things we talked about with the parameters, this is a transit scan, correct? Like a transit observation?
No, actually, it's a tracking observation. So, but it's a very short tracking observation because these galaxies are relatively close by. And so now some of them, when I first did this exercise, about a year ago, right after the last year's Eastern Conference, when I first got access to this, I went on a safari hunt and I eventually ended up capturing 30 of the things galaxies using this method. So when I got to the farther ones, the ones that I worked my way down the list from brightest to dimmest. So when I started getting to the dimmer ones, I had to start dialing up the amount of time on target because I needed more integration time to get the signal to come out of the noise. But the brighter ones, literally, uh, you know, 5 seconds on, 5 seconds off was all we needed to get a good clear spectrum. Um,
They choose that observation time. Was it just trial and error?
Yeah, kind of. So the first time, yeah, it really was trial and error. So what I did the first time, it was way overkill because I didn't have any idea how short, how long or short it needed. So I started out with like 2 minutes or something, and it was super clear. And then I thought, well, I wonder what 30 seconds will look like. And then I basically did an experiment where I did the same observation of M101 over and over with shorter and shorter integration times. And I found that even with 1 second on, 1 second off, it was really noisy, but I could still see it. And I was like, wow, that's that is pretty impressive. And so, yeah, it is a tracking. We are tracking it, but like I said, we're only tracking it for a very short amount of time. So it's not like a pulsar observation where you have to stay on it for quite a while to get it. These are fairly relatively actually relatively bright signals compared to like pulsar observations. So until you get to some of the ones farther down the list, and then I had to go up to like 30 seconds or a minute. And then once I started getting above that level, it got to where um, like I was trying to I tried to do an observation of the Leo triplet, which the those are close enough together that you almost can't separate them because they're all kind of in the half power beam width of the dish at that point. But I even with like 2.5 minutes or so on target, I couldn't get a spectrum for those, and I didn't want to waste a bunch of credits trying to spend a whole bunch of time on target. At some point, I might see, if it might be interesting to see if we could actually get those to come out of the data, but it would probably take quite a bit longer on target to get those because there's
Jason, yeah, a couple other questions, but just as a follow-up, just from a learning perspective, for those galaxies that do require longer, because the signal's weaker, you need longer observation time. But for those that are shorter, why would I choose tracking versus just do a transit if it's a short observation time? Do you have any pointers on that one?
not really. I mean on off mode just seemed to be the perfect choice for what we were trying to do. Um, uh, I honestly I didn't realize that you could do a transit mode with this dish. I just
Yeah, the question is not well founded. I haven't used the 20 meter. I'm just used to the 40 foot. So that's why I was just wondering. With that we do a transit. So I was wondering if I could do a transit with the 20 meter. Why would I choose to do a track?
Yeah, I don't I didn't see transit as an option on it, but then again I've only like it's interesting. I've only used a few features on it, so I don't necessarily know. I only know what I've used. So, but I do know that like when I do backyard observations with my smaller setup, I definitely do transit because I don't even have the option for tracking. In fact, my backyard scope was literally made from plywood and PVC, and it didn't have any kind of motorized mount or anything. I literally set it by eyeball, and it was completely drift scan only. So, but you know the process is basically the same for these types of observations. If you're not using transit, in this case, you just do 1 point on, 1 point off, and but you do the math the same way in the post processing, where you just take on target, subtract the off target, and that gives you your resultant spectrum. So
Thanks, Jason. There's another question.
Yeah, hi, Jason. Were any of your observations through the plane of the Milky Way? And if so, how did the different Milky Way arms at different velocities affect your results?
The answer is no, because none of the galaxies we were observing are in the plane of the galaxy. Some of them are, closer to the plane than others, but none of them are actually in the plane. But the question, theoretically, though, if we were observing one in the plane, the the result would, or the process would be exactly the same, and the result would be the same in that if you look at how much if you look at the spread of the in-plane observations for the Milky Way, even the ones where you're looking across multiple arms and they're Doppler shifted, significantly from zero, they still only range plus or minus 50 to 75 kilometers a second at most. So they all stay very relatively close to zero, where even with the exception of M81, most of these galaxies that we're looking at are redshifted significantly out of the velocity range of even the most red or blue shifted arms of the Milky Way. So they're usually more than 100 to 200 kilometers a second, or even more, out redshifted. And then for the case of the local group, the ones like M31 and M33, those are blue shifted, but they're significantly blue shifted. They're in the range of 2 to 3 to even like in the case of M31, the highest blue shifted part of the spectrum is close to 600 kilometers a second negative. So it's way outside of the range of any of the Milky Way signals, because those are, even though they're red shifted and blue shifted because of their motion, that the speed of that motion is less than 100 kilometers a second plus or minus. So
All right, thank you very much for that.
Can I have one more question, please?
Yeah, sorry, before you do, can I just butt in? Sorry, I've just been looking up on the Skynet there, the question of whether there's the option to do a transit, and actually the only options that come up are track, map, daisy, and on-off. There's no transit option on it.
Okay, very good, thank you. You can stop sharing now, Andrew, and we appreciate it. And we'll be back online.
Can I have one last quick question, please? Jason, when you plot the data points, are you plotting just one of the feed poles, or you just pick one and ignore the other?
Actually, what I do, because you're right, there are two polarizations, orthogonal polarizations, and I actually average the two together because these integrated spectra are randomly polarized, and so it kind of gives you twice the integration time. So I just average the two together.
Great, that's fantastic. Thank you.